Good morning, dear students. Welcome back. Today we are studying a new chapter as well as new unit, that is electronic device, having a weightage of 7 marks for CBSE purpose. All about approximately 12 periods be there in this particular section. 2 experiments as well as 3 activities are in our syllabus concerning with this particular chapter. It's a very important aspect or very important unit for our further studies, just like whenever we are going for engineering side, just like electronics and communication, CS as well as IT. Exactly, we are dealing here some electronic devices which are very useful in our daily life, as well as some basic concepts of electronics. Dear students, as usual, at all first, we want to share here syllabus. What syllabus we cover in this particular chapter? Chapter name according to NCERT, that is semiconductor. And here we would like to study about electronics. What is electronics? Then materials, devices and simple circuits. That's the first part. Then after we will have a look about energy bands in conductors, in semiconductors and in insulators. Exactly, I used here, have a look, as we are discussing here only qualitative idea, not quantitative. Then after we will discuss here semiconductor diodes, voltage and current characteristics in forward biasing and reverse biasing. A diode may be connected in two types, just one forward bias and reverse bias. We will discuss it in later. Diode as rectifier, there is a use of diode, a very fabulous use. Diode as a rectifier. Whenever we want to convert AC into DC, then we have to use a diode, and that particular use of diode be termed as diode as rectifier. Dear students, then after we will discuss in this particular chapter special purpose PN junction diodes, just like LED light emitting diodes, photodiodes, solar cells, then Zener diode and their characteristics. And we have to learn here how to a Zener diode is used as voltage regulator. That's our theoretical syllabus which we will cover in this particular chapter or in particular unit. Dear students, we are going for explaining some experiments which are in our syllabus to draw current potential characteristics curve for a PN junction in forward bias and reverse bias. The same concept as we have done in theoretical classes. Then after experiment number 9, to draw characteristic curve of Zener diode and determine its reverse breakdown potential. These two practicals be done in our lab. Then some activities only for the demonstration purpose. Number 1, to identify a diode, LED, resistor, capacitor from a mixed collection of such items. Somewhere we have a collection of these simple devices. Then we have to identify which one is diode, which one is LED light emitting diode, which one is resistor and which one is capacitor. Then the next, we will learn here how to use multimeter to see here unidirectional flow of current in case of diode and LED, and how to check electronic components just like diode is in working order or not in working order. Then next activity to show, that is we have to show here effect of intensity on LDR. LDR stand for light detecting resistors. Thereafter, we would like to start our syllabus. At all first, I want to discuss about what is electronics. Dear students, electronics is a branch of physics in which we deal about some electronic devices. What about some electronic devices? Exactly any device whose action is based on controlled flow of electrons. If we control the flow of electron in a particular device, then such device we termed as electronic device, and the study of these electronic device we termed as electronics. Dear students, in electronic devices, some basic building blocks or some electronic circuits are there. We have to study here. Some of important features of the semiconductor devices are as follows. We are studying in previous chapters about some electrical devices, but somewhere electronic devices are quite differ, or semiconductor devices are quite differ than that of those. We would like to state here some features, just like in a semiconductor device, simple excitation, light, heat or a small applied potential can change the number of charge carriers. Whenever we want to flow some charge through a conductor, there is a need of some charge carriers. In semiconductor devices, the charge carriers number may be controlled by normal excitation, just like by light, by small heat or whatever so small potential. Thereafter, the use of semiconductors to develop junction diodes and transistor has a great advancement in electronics. Exactly in all our gadgets, just like mobile phones, computers, laptops, building blocks are semiconductor diodes or junction diodes as well as junction transistors. Exactly, we have to study here about junction diodes. How we will manufacture diodes and how we will use them in gadgets, we will study in further classes. Dear students, but these two applications or two characteristics are very important to describe utility of semiconductor devices. Semiconductor devices are very small in size, they consume very low power and it may be operated at very low voltage. They have long life and high reliability. Up to a long life, they are reliable. Dear students, these are some characteristics or usefulness of semiconductor devices, why we are using in our new gadgets. Classification of solids on the basis of their electrical properties. Exactly, before seeking some information about semiconductors, we would like to classify different materials in three parts. There may be insulators, conductors, and meanwhile in between insulator and conductor, semiconductors are there. Dear students, we may classify them on the basis of resistivity or may on conductivity. At all first, we are taking here metals with certain characteristics. Some more characteristics are there. Exactly, the resistivity of metals is very low. It is of order 10 to power minus 2 to 10 to power minus 8 ohm meter. Just like conductivity is comparatively very high, that is 10 to power 2 to 10 to power 8 Simon per meter. Then after we would like to share here insulators. Insulators have a great resistance or resistivity, that is more than 10 to power 8 ohm per meter or ohm meter, sorry, and conductivity be very little, just 10 to power minus 8 Simon per meter. In between metals and insulators, semiconductors comes. Their conductivity is more than insulators but less than metals. Then they are very useful to control potential or currents on behalf of charge carriers. The conductivity of semiconductors is between 10 to power minus 5 to 10 to power 0 Simon per meter, just as the resistivity belongs to order 5 to 0 ohm meter. Semiconductor have a temperature coefficient resistivity that is both negative and high. Dear students, whenever we change the temperature of semiconductor, its resistance gradually decreases or gradually increases. This is the significance of temperature coefficient. We have already discussed in current electricity how they vary. Whenever we change a very small change in temperature of a semiconductor device, its resistance at first decreases, then after it increases. Just for a shake or to recall, we may plot a graph, temperature and resistivity, just like that. That is the resistivity and then the temperature. At a particular temperature, resistivity is here very low, and less than this particular temperature, resistivity gradually increasing, as well as after attaining this particular temperature, resistivity gradually rises. That is a simple concept in between resistance or maybe say resistivity and temperature of semiconductors. Just for recall, we have discussed all these things in current electricity, dear students. Then after I want to classify the semiconductors on their nature, on their occurrence. First one is elemental semiconductors. Those semiconductors which are in form of element or they are pure. There is no compound or there is no mixture. Examples: silicon and germanium. These are elemental semiconductors. Then after we would like to state here compound semiconductors. Dear students, there are so many compound semiconductors. Again, compound semiconductors may be rearranged in inorganic and organic. Inorganic compound semiconductors are CDS, cadmium sulfide, gallium arsenide, cadmium silicate, and whatever, so indium. Just like organic polymers, polypropylol as well as polythiophene. These are the some examples of organic polymers. Then we would like to classify semiconductors on behalf of source and nature of charge carriers. Dear students, charge carrier may be of two types. Number one, that is electrons, very familiar, and number two, these are holes. Holes, a new concept is there. Exactly whenever a electron transferred from one plot to another place, then there is an empty place of electron that is termed as hole. Exactly, hole is nothing. That is the empty place of electron. Dear students, as electron charge carriers have a negative charge, then hole charge carriers have a positive charge. When we want to discuss the motion of electrons and holes, they are in opposite directions. If electron is moving in left direction, then hole will move in right direction or vice versa. On the basis of charge carriers, we would like to discuss or categorize types of semiconductors. First one is intrinsic. Intrinsic stands for pure. Semiconductors which are pure, there is no impurity, are termed as intrinsic semiconductors. Exactly, in intrinsic semiconductors, impurity is very little, just like 1 part in 10 to the power 10. That's a negligible. Dear students, in intrinsic semiconductors, electrons and holes both are charge carriers, but are in very small extent. At room temperature, intrinsic semiconductors have a very low or very little conductivity, hence they are not used in general at room temperature. Dear students, then after we want to state or explain the structure of an intrinsic semiconductor. It may be just like germanium or it may be silicon. As we all of know, the valency of silicon as well as germanium is 4. Hence why in outermost orbit 4 electrons be there. Dear students, in general, or all 4 electrons make a covalent bond with other one like that, but somewhere there are some point defects, there are some comparatively weak covalent bonds, hence they break at normal temperatures, and somewhere very little amount of electrons as well as very little amount of holes is available for conducting. In an intrinsic semiconductor, number of holes is exactly equals to number of electrons, hence why electronic currents or currents flown with the help of electrons is almost equal to hole current or current flown through holes, and the total current must be equals to the sum of electronic current as well as the hole current. Dear students, as we already discussed the limitations of intrinsic semiconductors, semiconductors have a very less or very little conductivity at room temperature. That is the first limitation. Very low number of charge carriers. Just here it is defined 10 to the power 4 per meter cube. Hence why they have a very low electrical conductivity. And again, dear students, intrinsic charge carriers are always thermally generated. As we rise temperature, some charge carriers are free to move and the flexibility is not available here, as we can control everywhere all time the temperature. Dear students, for intrinsic semiconductors, as we have discussed, number of electrons is equals to number of holes. They cannot have predominant hole or electrons for conduction. This put a limit that usefulness of such materials. As a whole, I may say or we may say intrinsic semiconductors are not useful in our daily life. Dear students, then another type of semiconductor is extrinsic. Extrinsic semiconductors have a comparatively more impurities, and by some a particular manner we have to do some impurities in an intrinsic semiconductors, hence why it will be termed as extrinsic semiconductor. According to our need, we have to increase the number of charge carriers in extrinsic semiconductors. Dear students, what's doping? Exactly, doping is a process by which we have to increase charge carriers in a intrinsic semiconductor, or we may say doping is a process by which we may add some impurities, suitable impurities in intrinsic semiconductor to raise the number of charge carriers. Dear students, what we have to define in our examination, in order to increase the conductivity of pure semiconductor or intrinsic semiconductor and to overcome their other limitations, a small amount of impurity atoms having valency different from 4, as our intrinsic semiconductor just like silicon and germanium have a valency of 4, hence why we have to add some different element which have valency 3 or maybe 5. Trivalent or maybe pentavalent impurity must be added in an intrinsic semiconductor to achieve a particular conductivity or a particular number of charge carriers. Dear students, doping process is entirely depends on size of the dopant atom. The size of dopant atom must be almost same as doped element. Dear students, for the purpose, atoms of third and fifth group in periodic table are most suitable. Concentration of dopant atom should be small, about 1 part per million. Again, here we dope or we add some impurities, 1 part out of 1 million. Dear students, I want to again discuss about the holes. The vacancy or absence of electron is termed as here hole. Vacancies have a positive charge and is called hole. Again, hole doesn't exist as a physical entity, just like it's a empty space of electron. Dear students, I want to categorize or characterize the holes. Categorization is not appropriate word. Exactly characteristics of holes. A hole is just vacancy, as we have discussed. It has the same mass removed of electron. It is associated with positive charge equal to magnitude of E or electronic charge, that is 1.6 into 10 to the power minus 19 coulomb. We all of know charge on electron is with negative side 1.6 into 10 to the power minus 19 coulomb. But charge on hole is plus 1.6 into 10 to the power minus 19 coulomb. That's the concept here, students. Energy of hole is higher. Exactly whenever we are to compare the energy of electron and hole, then hole have a higher energy. Extrinsic semiconductor, after doping or after mixing impurity in intrinsic semiconductor, we find extrinsic semiconductors, as we discussed earlier. Here the density of charge carriers increases as we dope. Extrinsic semiconductors may be two types. Number one, N type. N type stands for negative type. Extrinsic semiconductors which have majority charge carriers electron, or we may say negatively charged particles, they will be termed as N type semiconductors or N type extrinsic semiconductors. The extrinsic semiconductors which have majority charge carriers positive or maybe whole be termed as P type or positive type extrinsic semiconductors. Dear students, how we gather N type semiconductor? Exactly, a tetravalent intrinsic semiconductor just like germanium is doped with a pentavalent impurity. Pentavalent impurity may be phosphorus, arsenic. When we add this impurity, then scenario be like that. These are the 4 electrons. They may make a covalent bond with corresponding electrons, but the 5th electron of phosphorus, as it is pentavalent, just it may be here, left vacant. This vacant left electron may move inside extrinsic semiconductor. Hence why per doping nucleus one electron is left for carrying charge. Hence why the number of charge carriers increases here. As a whole, number of charge carriers, negative charge carriers is more in a n-type semiconductor. But what about the total element or total atom? Exactly, dear students, we doped here a neutral phosphorus in a neutral germanium. Hence why there is no net charge on germanium phosphorus mixture or doped germanium. It is again very important aspect. There is no net charge on n-type extrinsic semiconductor. Dear students, the same figure is again redrawn here. One electron is here unbonded, that is termed as free electron, which is free to carry charge. Hence why the conductivity of n-type extrinsic semiconductor increases. Then after, dear students, we want to discuss formation of n-type semiconductor by doping tetravalent silicon with pentavalent impurity. The same process is here. At room temperature, there is a number of adequate charge carriers. Here electrons are again majority charge carriers. Here we have discussed number of electrons is comparatively more than number of holes, or number of holes is comparatively less. Then I want to discuss about formation of p-type extrinsic semiconductor. Dear students, almost the same process, but impurity chosen here is from trivalent. As we discussed earlier, a germanium or a silicon tetravalent atom is doped with trivalent aluminum, or it may be another, just like gallium or boron or indium. 3 electrons are in outermost orbit. Exactly 3 covalent bonds are formed with aluminum to germanium, but the 1 electron of germanium which are comparatively strongly bounded with germanium are left here. Hence we may say, in other words, a hole, a deficiency of electron is inside a doped atom. Dear students, here positive charge carriers or holes are comparatively more than that of electrons. Hence why they are termed as positive type extrinsic semiconductors. Dear students, again, as a whole, there is no charge or net charge is 0 here, as neutral germanium is doped with neutral aluminum. But the number of charge carriers is more here compared to intrinsic semiconductor. That's our another type or p-type extrinsic semiconductor. How it is formed we have discussed here. With the same diagram we have explained here. Creation of hole. Free electrons are only due to thermal generation, but holes are majority charge carriers here. Number of holes is greater than number of electrons. Again, note down, it may be noted that doping does not disturb overall charge neutrality of the semiconductor. Dear students, I hope so you have understand all the things. You have to done assignment provided with this class, very few questions which are all conceptuals in nature be done. We will discuss energy bands in solids in our next class. Thank you, dear students. Keep safe, be safe.